the new phenology model that we've built into APSIM, I'm going to talk now specifically about the structure and how we've implemented it. So it all came about because there's this piece of work that Ian Brooking and Pete Jameson conducted measuring phenology of a couple of genotypes of wheat in controlled environment. It's a really nice study, and I thought it'd be good to run APSIM against it. And I ran APSIM against it, and it couldn't come anywhere close to predicting any of the phenological responses. And so I sort of thought it through, and the end result was this paper that we wrote in Annals of Botany, sort of linking up the typical physiological approach that we tend to take to modelling anthesis with some of the molecular biological approaches. So we've called the model CAMP, which is an acronym for Serial Anthesis Molecular Physiology. It's nothing to do with the pop culture reference to CAMP that some of us will be familiar with. So the molecular approach to explaining flowering time generally looks something like this. So you have a model where people will have done a whole lot of detailed work to understand the genes that are controlling progress towards anthesis. And so in cereals, there's three main genes that are controlling things. There's VERN1, which is the gene that controls the transition of the apex from a vegetative state into a reproductive state. And so VERN1 needs to be upregulated to a certain level for floral transition to occur. VERN1 responds directly to cold, so cool temperatures will cause VERN1 to upregulate, and that's what gives us the vernalisation response that we see in a lot of crops. VERN3 is sensitive to photoperiod, and it promotes VERN1 expression. So in longer photoperiods, VERN3 will upregulate and cause faster regulation of VERN1, expediting our progress towards floral transition. And so that's what gives us the classic photoperiod responses we see. In some genotypes and cereals, we also have VERN2, which is causing confusion to the situation, basically. So VERN2 is also upregulated by long photoperiod, the same as VERN3, and it blocks VERN3 action. So when VERN2 is there, it stops VERN3 upregulating VERN1 and giving us floral transition, but VERN1 blocks VERN2. So when you've got VERN2 present, it sort of exacerbates the need for vernalisation response at longer photoperiod, but then at shorter photoperiod, it goes away. The physiological approach, which most of the APSIM modelers would be more familiar with, is sort of your phasic development approach. So we break the process of floral transition into a series of phases that the crop goes through, and we look at the environmental controls on each phase. So germination is influenced by soil moisture, emergence by sowing depth and temperature. Time up to vern saturation is influenced by cold and photoperiod. Time through to terminal spikelet then is influenced by temperature and photoperiod. The time from terminal spikelet to flag leaf is influenced by phyllochron, so leaf appearance rate, and temperature, which drives leaf appearance rate also. And then flag leaf to heading is also influenced by photoperiod and temperature. And then heading to anthesis is just driven by temperature. And so what we've done in CAMP is actually combine these two approaches. So we've taken the typical phasic development approach and combined that with the concept of a molecular model with temperatures and photoperiods driving vern expression that influence your progress through these phases. So in particular, from germination to vern saturation, we have a target for Vern1 to be expressed up to, and then temperature influences the rate at which Vern1 is expressed. When we reach that target, Vern saturation occurs, and then we go into the next phase where Vern-free expression is occurring, and we have a target for Vern-free expression as well. And once Vern-free is expressed to that level, it means we'll have sufficient upregulation of Vern1 to achieve terminal spikelet. So that's the differentiation of spikelets on the apex. When we consider the role of Vern2 in the process, so in this example again, we've got Vern1 expressing at the same rate. We've got our target here, but then because Vern2 needs to be blocked by Vern1, when Vern2 is expressing, the amount of Vern1 we need to express increases. And so we've got this dotted red line here is potential Vern2 expression, and our actual Vern2 expression is this one here because the potential is being blocked by Vern1. And once we get to a situation where all of the Vern2 is blocked, we'll then have Vern-free expressing, and it can express and kick the Vern1 up to the levels we need for terminal spikelet to occur. So just a few examples here, and apologies, these graphs are a little bit messy, but to demonstrate just how the model captures responses. So in these examples here, I'll have two panels just with two scenarios above and below. They all have apparent Vern expression on the y-axis, and the x-axis is in horn stages with phenophases marked when they occur. So in this case, we've got the same genotype, Batten winter, and in the top example, it was grown for a period at 6 degrees in the dark in this case, which is a bit silly, but anyway. And during this cold period, we've got Vern1 expressing relatively quickly, reaching the target, and then at a horn stage of 2.5, and then Vern-free starts expressing, and we reach terminal spikelet at a horn stage of 5. So that's with 5 leaves expanded, and flag leaf occurs with 8 leaves on the main stem. If we compare this to an alternative scenario where we've just grown Batten winter at 23 degrees, we can see that the Vern1 expresses a lot slower, and it gives Vern2 a chance to start expressing, which pushes the target out even further. And so we don't reach Vern saturation until a horn stage of 10, and then terminal spikelet at 12, and we grow through to 16 leaves. So that's how the model captures vernalisation response. It's through the temperature driving the speed that Vern1 comes up. The way it captures Vern sensitivity, so differences between cultivars, looks something like this. So on top, we've got Batten winter again. That's the scenario we looked at before. And on the bottom, we've got Batten spring, which is an isogenic line for winter Batten, but it doesn't have a vernalisation response. And so it expresses Vern1 quickly, regardless of the temperature. So at 23 degrees, the Vern1 expression comes up and reaches the target at a horn stage of 2.5, and then we reach terminal spikelet and flag leaf much quicker. So this is how the model captures vernalisation sensitivities. It's basically through how quickly a genotype will express Vern1 under warm conditions. Anything that expresses at a high rate under warm conditions is what you might call a spring wheat, so it won't demonstrate a strong vernalisation response. And then we have photoperiod response. So in this example here, we've got a genotype called McCubbin, grown at 16 hours on the top and 8 hours on the bottom panel. So on the top here, we've got a bit of Vern2 activity happening here. So Vern2 is expressing up, then Vern1 down regulates it once the Vern2 is all blocked, we'll start to see Vern-free expression, and we'll reach terminal spikelet at a horn stage of 5 and have a flag leaf of around 8. If we go to 8-hour photoperiod, we don't have Vern2 expressing, and so we reach Vern saturation actually a little bit sooner because we haven't got Vern2 delaying things at a horn stage of 1.6. But then our Vern-free upregulation is a lot slower because we're in a short photoperiod, and in this particular genotype, it takes us through to a horn stage of nearly 12 to reach terminal spikelet, and that gives us quite a large final leaf number. And then the genotype sensitivity to photoperiod is demonstrated by these two comparisons. So on the bottom is McCubbin again, which is what we looked at previously. On the top is Otani, which is a true spring wheat. Shows very little photoperiod response. And so even under a short photoperiod, it upregulates Vern-free quickly and reaches terminal spikelet. At a relatively early stage and has a much smaller final leaf number compared with McCubbin. Okay, so in terms of implementation in the APSIM framework, this model has been built in plant modeling framework and appended into the wheat model that's in release. So the changes we're talking about are only to the phenology model. Thermal time is the primary driver, and it's calculated using the same thermal time profile that's in the existing model, except we've changed it to use a free hourly interpolation during the day rather than the old sinusoidal approach. This one uses a sine curve during the day and then an exponential decrease during the night, and so it can give you a better representation of the effects of diurnal temperature variations in sort of shoulder environments. Phylacron is important for this model because gene expression is calculated relative to Phylacron, and the expression rate parameters are all relative to leaf appearance as well. So Phylacron is quite important. Phylacron is calculated the same as it is in the model in release. So it's the product of a base Phylacron, which can vary with cultivar, and a leaf stage factor. So the leaf stage factor is below 1 for the first couple of leaves, which means they appear quicker, and then sits at 1 up until leaf stage 7, and then jumps up to 1.4. So any leaves appearing after leaf 7 will appear slower than the earlier leaves, and this is something we see fairly reliably in experimental data. Then we also have a photoperiod effect, and so the photoperiod effect looks a bit like this. On short photoperiods, less than 12, we can see a response. So we have the photoperiod effect as a sum, so it's the sum of 1 and then a photoperiod sensitivity, and this can be 0, which means you don't get a photoperiod effect, and it can increase to any value, but generally the numbers we see in genotypes are below 1. And so if you had a value of 1, it would mean at a photoperiod of 8 you would double your Phylacron, although generally the numbers we see are about 0.3. Okay, so then we go through the phases. So we've got a germinating phase, an emerging phase, and then a vernalizing phase. So this vernalizing phase is a new class that we wrote specifically for this model. And basically the plant sits in the vernalizing phase, and it will complete and progress to the next phase when Vern1 expression is above 1. And when Vern2 expression is 0. So in cases where Vern2 may be expressing, Vern1 expression will have to go higher than 1 to block it out and allow vernalization to occur. We then go into a spikelet differentiation phase, which completes when Vern3 expresses up to a value of 1. And so this is driven by photoperiod. Longer photoperiods give us faster expression. And so this phase is photoperiod sensitive as a result. And we then have a stem elongation phase, which goes from terminal spikelet to flag leaf. And basically we complete that once the number of appeared leaves reaches the predicted final leaf number. And CAMP does the work of predicting the expression of Vern 1, 2, and 3 and what the final leaf number is. And so in the model, we've got this CAMP class included now as well, which is doing the bulk of the work. And then we go into a head emergence phase, and an important distinction with the old model here is that, or the existing model in New Gen, is it didn't have a head emergence phase with a prediction of heading. It predicted only anthesis, so we've added the prediction of heading in. And heading is predicted as a target under long day. So under long days, heading will be at its shortest duration. And then we will add in a short day extension. So under short photoperiods, it can take longer to get from flag leaf to heading. But that is genotype specific. So this photoperiod sensitivity is set for each genotype. If it's a value of 0, we see no photoperiod sensitivity, and it can be a value of well, any number, and the higher it is, the more sensitive the genotype is to photoperiod in this phase. Okay, so in terms of the expression, the gene expression rates, Vern1 expression is calculated per horn stage, so it's relative to leaf appearance, and responds to temperature. So at low temperatures, we see higher expression rates relative to horn stage, and then as temperature increases, the rate of expression declines. And the two lines here represent different genotypes. So a genotype that is that doesn't show vernalisation sensitivity would drop away slower than a sensitive genotype. So sensitive genotypes at high temperatures don't express Vern1 as quickly, and so their development will be delayed. So these curves are described by a couple of parameters, the max Vern1 expression rate and the base Vern1 expression rate. For photoperiod, again, we've got Vern-free expression here relative to horn stage plotted against photoperiod. And we see this response that as photoperiod declines, the rate of Vern-free expression declines. And the free lines here would represent free genotypes of different sensitivities. So if you have a high value for min delta Vern-free, you would show low sensitivity. So you'd be expressing Vern-free at a relatively high rate regardless of photoperiod. But then sensitive genotypes would have a lower value for min Vern-free. And we can put Vern2 on the same graph because it also responds to photoperiod. And we assume that at a value of a photoperiod of 8, we're not getting any Vern2 expression. And as photoperiod increases, Vern2 expression increases up to a maximum rate. And so these parameters here are what link to the sort of the typical development behaviors we'd see in different genotypes. So the max Vern1 and the max delta Vern-free relate to earliness per se. So in conditions where you receive full vernalisation and long photoperiod, you'll still get differences in how quickly genotypes develop, and those differences are quantified by these two parameters. Then this min Vern-free parameter represents photoperiod sensitivity that we see in different genotypes. The base Vern1 represents vernalisation sensitivity, and the max Vern2 represents the interaction between photoperiod and vernalisation sensitivity. We did for a while call that short day vernalisation, but we're actually seeing that long day is interacting with vernalisation as well. So we're sort of going away from the use of the term short day vernalisation now. And so I just put this graph in here, and Enley's already talked about this, so I won't dwell on it. But basically we can use controlled environment experiments to quantify leaf numbers under a prescribed set of conditions, and from these we can derive the expression rates that I've talked about here. I think I'm going to pass on to Neil, and we can have questions, but something I probably should point out is, although I've talked about expression rates as though they're something real, they're actually abstract in this model. So we don't have a lot of good data where we've measured expression rates through time in response to different environments to calibrate the model. So the response patterns are all assumed, but they're assumed to reconcile a fairly substantial base of experimental evidence. So, yeah.